Welcome to a new video heat transfer. Today we start talking about convection. Up to this point we already classified the three different heat transfer processes. So we have talked about, of course, conduction, and conduction is the heat transfer mechanism where there is no bulk motion. It requires a medium and it can occur in a solid, liquid or gas, and is due to the vibration of the molecules of the medium and also due to the transfer of free electrons. Instead, in convection, the velocity field is not zero, so there is a bulk motion. It also requires a medium and it occurs in liquid and gases. It also due to the vibration of the molecules of free electrons, but the most part of convection is due to the motion, the bulk motion of the fluid. And also we are talking about radiation, and radiation is of course due to electromagnetic waves. And one of the main differences from conduction and convection is that radiation does not require a medium to operate. So let's talk a bit more about convection. The first central idea is that in convection, the bulk motion enhances heat transfer. So this bulk motions basically brings hot part of the fluid in contact with cold parts, and this interactions due to the mixing generates very high gradients of temperature. And in turn, of course, we know that the higher the temperature gradients, the higher is the heat transfer. And in general, the higher the velocity field, the higher the heat transfer. Let's look about these three examples. We have air, we have cold air, and cold air is in touch with the surface, a hot surface. So we always have heat transfer from the surface to air in all these three cases. But the heat transfer mechanism is quite different. On the left here, we have a conduction problem. So air is not moving. We still have heat transfer, of course, by conduction from the surface to the air. But imagine now we have a situation where we have free convection, which means that the temperature gradients induce some density gradients, then impact on the momentum. So a fluid motion occurs, which is free. So meaning it's not imposed from the outside. And this is also called natural convection. In the third case here, we have a case of forced convection. Now, in the forced convection, the motion of air is due to an external agent, in this case a spinning fan, for example. So in general, we have that the forced convection, the heat transfer coefficient is larger than free convection. And free convection is has a larger heat transfer coefficient than conduction. Another example is a classical case of two plates, parallel plates. The top plate is hot, in this case 110 degrees Celsius. The bottom plate is cold at 30 degrees Celsius. We have a fluid in between, and so we have heat transfer from the top plate down to the cold plate. So imagine we keep the same delta T, we see the same jump in temperature from the hot plate to the cold plate, but we vary the velocity. Well, we observe that increase in the velocity, so increase in the Reynolds number of the flow between the plates, has the effect of increasing the heat transfer. So the larger the velocity, the larger the heat transfer for the same temperature jump. So we have to now ask ourselves a bit more in detail, how does the convection heat transfer depend on? So in the case of conduction, we now know that heat conduction depends on, of course, the thermal conductivity, the surface area, and the gradient. Here I've written in one dimension, but we know very well that Q is in general a vector, so this can be interpreted as the gradient in 3 dimensions. And this is the Fourier's law of conduction. So in conduction, heat transfer depends on the property of the fluid through the thermal conductivity and to the temperature gradient. But in convection, the situation is more complicated because Q depends on many factors. Depends on the fluid properties, for example, the dynamic viscosity, the thermal conductivity, the density, and the specific heat. It also depends on the fluid velocity field and on the regime, for example, whether the flow is in laminar, transitional, or turbulent. And also depends on the system geometry and on the surface roughness. Mathematically, we can express the heat due to convection in this form, thanks to the Newton's law of cooling. The name is slightly deceiving because it's called Newton's law of cooling, but actually valid for heating as well. Q convection is equal to H, the heat transfer coefficient, times AS, the surface area, and the jump in temperature between the surface temperature Ts and the temperature of the fluid at T infinity. So represented schematically here. So what are the objectives or study of heat convection? We have 2 main objectives. First of all, we want definitely understand the physics of the fluid motion. So we want to gain a great understanding of fluid mechanics in relationship to heat transfer. So we want to understand how the fluid motion changes the heat transfer mechanisms in the system. And the other objectives is, of course, to determine H. Up to this point in our study, H was a given quantity. But now, thanks to a more specific analysis, we can find ways to determine H. H depends on the fluid properties, but as I said before, strongly on the fluid motion. So what happens near the surface? If we analyze the system under a fluid mechanics point of view, we know that the no-slip condition occurs for the velocity. So the velocity profile along the streamwise direction has this form. So in the laminar case, but also similar in the turbulent case, if you consider average properties. And the particles stick to the surface. So they have the same velocity of the surface. And this condition is called the no-slip condition. The temperature obeys a similar condition called the no-jump temperature condition. So here I've sketched instead the temperature profile in the case where the plate is very hot and the fluid away from the plate is colder. So in this situation, the temperature of the particles at the surface is the same as the temperature of the surface. So there is no jump in temperature. So temperature is a continuous function of space. So because of these 2 conditions, it follows that conduction occurs at the surface because the fluid particles that stick to the surface, so they have no velocity. So we can write that the Q conduction at the surface is equal to Q convection, and since Q conduction can be written in this form thanks to Fourier's law of conduction, so minus K thermal conductivity of the fluid times the gradient of temperature along the wall normal direction. Then heat is taken away by convection because of fluid motion. And we can imagine then it's very difficult to measure directly this temperature gradient because usually we have very high gradients of the temperature. It's very hard to measure the temperature at location very close to the surface. we can now combine the Fourier's law of conduction for the particles that stick to the surface with this expression, which is for Newton's law of cooling. So Q conduction equal to Q convection. We can set it equal to each other, and we have the definition of H. So H is equal to the ratio between minus K of the fluid times partial T partial Y. So the gradient of temperature with respect to the wall normal coordinate computed at the surface, divided by Ts minus T infinity, where, remember, Ts is the temperature of the surface and T infinity is the temperature of the fluid sufficiently far away from the surface. Of course, we always like to study heat transfer in non-dimensional terms, so we introduce a very important non-dimensional number called the Nusselt number. The Nusselt number is equal to H times LC divided by K, where H is the convection coefficient, LC is the characteristic length that represents the system, and K is the thermal conductivity of the fluid. We have to be careful because the BO number was also defined as H times LC divided by K, but in the case of the BO number, we were dividing by the thermal conductivity of the solid, whereas here we divide by the thermal conductivity of the fluid. So we can interpret the Nusselt number. I think I'm missing a T here. Nusselt. We can interpret the Nusselt number as the non-dimensional heat transfer coefficient H. And what's the physical significance? Let's go back for clarity to the case of two parallel plates. So the top plate is a temperature at T2 and the colder plate is a temperature T1. These two plates are parallel to each other and a distance, certain distance L. So we have heat transfer from the top plate to the bottom plate. We have some fluid in motion here. So if we have some motion, then we have Q convection. So there's some convection, H times delta T, Newton's law of cooling. If instead the motion of the fluid is not occurring, so we have just Q conduction. There's no motion, there's no bulk motion, so just heat is transferred through the liquid or a gas by conduction. Then we have a K delta T divided by L. So the Nusselt number can be defined as the ratio between this Q convection, when there is bulk motion, divided by Q conduction, so the heat transfer when there is no bulk motion. So if you substitute these two quantities, then we get the definition of the Nusselt number. Therefore, we can understand now what the Nusselt number actually means. So the Nusselt number can be interpreted as the enhancement of heat transfer due to fluid motion with respect to conduction across the same fluid layer and the same delta T. What does this mean? It means that the Nusselt number, so, is a number non-dimensional. It tells us how much more heat is convected thanks to convection with respect to conduction for the same fluid, the same delta T, but when there is no motion, so there is conduction. So when the Nusselt number is 1, we just have pure conduction, so it's a limiting case, and it follows also that the Nusselt number can never be smaller than 1. Okay, thanks a lot. I see you in the next video.